Another approach of base flow separation is fixed-based method. This is a little more accurate than single-line method. Learn how it works here in hydrology. When we draw a hydrograph, there will always be two parts of the water. The one on top is the direct runoff, which we can use to run our water projects. And the one at the bottom is the base flow, which is the amount of water underneath the grade replenishing streams and rivers. How does fixed-base method separate the base flow? Using the same hydrograph, where the x-axis is time and the ordinates are discharge, draw the distribution curve from the given dataset. After knowing the start of the runoff, extend the line or curve right before the start of runoff. The extension touches the peak discharge. With the intersection at the peak discharge, connect the point to the end of runoff. So from the output, fixed-base method includes two slopes separated by the peak discharge data. Let's work on an example using this approach in base flow separation. Given the dataset, we are to determine the base flow and direct runoff per hour or DRH with assumptions that the start of runoff is at the 3rd hour and the end is on the 10th hour. With time given as per hour, it is best to place 1-hour intervals in the x-axis. The y-axis is discharge, where the highest is 345 cumex. So knowing this, we can place the proper intervals for the ordinates. Now identify the start of runoff, which is at t equal to 3 hours. Also, the end of runoff is at t equal to 10 hours. Extend the segment of 2 to 3 hours until it intersects the highest peak, which is at 7 hours. Also connect this point of intersection to the end of runoff, that's t of 10 hours. Next is to identify the ordinates of the extended line. This is through similar triangles. From segment of 2 to 3 hours, the y distance between the points is 160 minus 140, which is 20. So from similar triangles, we can say that 20 is to 1 as y is to 1, where y is the vertical distance of the mirrored triangle. Y is then solved as 20. After which, the base flow at t equal to 4 hours is then solved as the reference level of 140 minus 20, giving 120. At t equal to 5 hours, we take similar triangles, that is 20 is to 1 from the small triangle on the left, and equate it to y is to 2 hours, where y comes out as 40 cumex. So the base flow at 5 hours is 140 minus 40, giving 100 cumex. The same process is done with t of 6 hours, where the first ratio is 20 is to 1, and this is proportional to y is to 3, so y is 60. Then base flow at 6 hours is then 140 minus 60, which leaves 80 cumex. The last point for the extended line from t of 2 to 3 hours is that with 7 hours. The same ratio and proportioning is done, where the small triangle has 20 is to 1, and this is proportional to y is to 4, where y comes out as 80. Thus, the base flow at 7 hours is 140 less 80, which is 60 cumex. For the second line from the peak discharge to the end of runoff, it is easier to look for the ordinates. It is because the 2 points are already provided, where the lower point is 60 and the higher point is 110, which means the full y distance is 110 minus 60, which is 50. This distance is just divided equally among the intervals. Or you can also work with similar triangles just the same. That is y is to 1 hour as 50 is to 3 hours. The per hour y interval is then 16.67. So the base flow is taken from the lowest point of y elevation of 60. Since the base flow is higher, we add y of 16.67 to 60, giving 76.67 for t of 8 hours. The coordinate at t of 9 hours is then solved similarly as y is to 2 hours, and this is proportional to the full 50 is to 3 hours. Y is then 33.33, and the base flow at 9 hours is 60 plus 33.33, and that is 93.33 cumex. After completing all the base flow values, we can place them in a table, where 1 to 2 hours have no base flow recorded, as they are before the runoff. From T of 3 hours, the discharge is considered fully as base flow, so it is 140 cumex recorded. The succeeding base flows then are 120, 100, 80, 60, then going up with 76.67, 93.33, then the end of runoff has a base flow of 110. Next is to identify DRH, or the direct runoff per hour. This is just the difference of the precipitation with the base flow. So at the start of runoff, at T of 3 hours, DRH is taken as 140 less base flow of 140, leaving no direct runoff. The DRH at 4 hours is then 190 minus 120, giving 70. At T of 5 hours, the direct runoff is solved as 245 minus 100, resulting to 145. At T of 6 hours, DRH is the precipitation of 295 less the base flow of 80, and that leaves 215 cubic meters. The same process goes for T of 7 hours, where DRH is computed from 345 less 60, giving the highest DRH of 285 cubic meters. At T of 8 hours, DRH is 310 minus 76.67, and that is 233.33 cubic meters. At T of 9 hours, DRH is 250 less 93.33, that is 156.67. Then lastly, at T of 10 hours, DRH is 110 minus 110, which gives no DRH.